The final section in this unit is to discuss nuclear decay. So before we discuss nuclear decay, let's talk about isotopes. Remember that an isotope is an element that differs in its atomic mass. And we symbolize this with isotope notation, where X is the atomic symbol, A corresponds to the isotope's mass, and Z is the atomic number, which is sometimes just understood, meaning that carbon-14 can be seen as carbon-14 over 6, or simply carbon-14. We could write these out as the name of the element followed by its atomic mass. So while the atomic number stays the same, meaning the number of protons is staying the same, the mass changes, which hopefully you remember from baby chem, means that the number of neutrons is what's changing. In fact, even the term isotopes can be broken down further. An isotope is simply a group of nucleotides. A nucleotide is a unique atom represented by the symbol seen here. So any isotope of carbon would be a nucleotide of carbon. So carbon-13, carbon-12, carbon-14. Those are nucleotides of the isotope carbon. Many nucleotides exist in a state of instability, at least thermodynamically and kinetically. And when they exist in this instability, they undergo a process called radioactive decay in order to become more stable. In fact, of the known over 2,000 nucleotides, only about 280 are stable. And tin has the largest number of stable isotopes with 10 nucleides. Whew, that's a tongue twister. The stability of the nucleus is derived from the ratio of protons to neutrons. And remember that neutrons are the atomic mass number minus the atomic number. If you were to graph all the nucleides with their number of protons versus their number of neutrons, you would end up with a graph that looks like this, where there exists a line of stability, this black line through the center, where you find stable isotopes, where you have a stable ratio of protons to neutrons. For light elements, those near the beginning of the periodic table, there exists a line of stability that would be almost linear, a ratio of 1 to 1. However, once you reach heavier elements, that it begins to deviate from that linear line. And in fact, if you look, any element with a atomic number over 84 are all radioactive, and there exists no stability. Certain combinations of protons and neutrons seem to confer some sort of special stability. For example, nucleides with even number of protons and neutrons are often more stable than those with odd. Also, there are certain specific numbers of protons and neutrons that produce stability. These magical numbers, as they air quote in the air, are 2, 8, 20, 28, 50, 82, and 126, which parallels the stability from electrons given the noble gases. Nucleides falling above the line of stability will undergo a particular type of radioactive decay in order to decrease their neutron to proton ratio, whereas elements below the line of stability or zone of stability will undergo a different type of radioactive decay in order to increase their ratio. Lastly, elements that are above the 84 mark will undergo a third type of decay in order to become less heavy. So there are three main types of nuclear decay that you'll need to know. I'm going to show you 5, actually, because one's kind of just the background noise that goes with it. In alpha decay, an alpha particle is emitted, and an alpha particle can be symbolized one of two ways, either the Greek letter alpha or He, 4 over 2, because it's a helium nucleus. And this will happen to elements with an atomic number over 84. Because they're so heavy, they want to fall back down into the line of stability. So for example, americinium with a atomic number of 95 will undergo alpha decay and give off an alpha particle, which is a helium nucleus with a mass of 4, 2. So it has atomic mass of 4, 2 of which are protons. So the number of protons is going to decrease by 2. 95 minus 2 is 93. The mass is going to decrease by 4. 241 minus 4 is 237. There is a conservation of both the mass and charge in the form of protons. Got to make sure that that equals out. Elements above the zone of stability, which have more neutrons than protons, and they are not at one of those stable nuclides, will undergo beta negative decay, or just beta decay. In beta decay, a neutron, which is really a proton that has an electron attached to it, will release the electron that is attached to it and go back to being a proton. When this neutron releases that electron-like particle, which we call a beta particle, it goes back to being a proton. Beta particles are like electrons in that they have no mass and they have a -1 charge. So elements above the zone of stability will go closer to it, will go down in the nuclide, will go down on that nuclide table by bringing their ratio of neutrons to protons down. An example of this would be cesium becoming beryllium. Notice again that there is a conservation of mass and a conservation of protons. 37 equals 37 plus 0, 55 equals 56 minus 1. Elements below the line of stability will undergo beta positive decay, or positron emission. In this case, hold on. There we go. The nucleus releases an anti-electron-like particle, which is a positively charged, no-mass particle called a positron. And in this case, a proton becomes a neutron. So carbon 11 can become boron 11 by the emission of one positron. Positrons are anti-electrons. So essentially this is antimatter. Yes, the thing that powers the Starship Enterprise is a real thing, and this is where we are beginning to produce this. And in fact, if you saw Angels and Demons and they said when antimatter connects with matter, so when a positron hits an electron, they annihilate one another and convert into energy, that is 100% true. That is good science. So let's talk about what that energy is. Gamma radiation is a high-energy electromagnetic wave that accompanies some radiation. So whenever you have, well, not whenever, if you have some sort of nuclear decay, it is often accompanied by gamma radiation. And while alpha particles can be stopped by as little as a piece of paper, and beta, positive and negative, can both be stopped by as much as a cinder block, or as little as a sheet of lead, gamma radiation and gamma rays can only be blocked by sheets of concrete, or thick layers of concrete and water. And so gamma radiation is the most dangerous. The last two types of nuclear decay happen in very small amounts. The first is electron capture. Since protons are positively charged, they attract electrons to them. If those electrons actually do reach a proton, they are captured, quote unquote, by the proton, and the proton becomes a neutron. When this happens, it releases a large amount of energy in the form of gamma rays. That's an electron capture. Again, this happens in very, very limited and very unappreciated quantities. Another type of nuclear decay is spontaneous fission, where a very large massed nuclide will undergo a fission, literally split in half, into two approximately equal massed nuclides. But again, this happens in a very small quantity to be spontaneous. As chemists and as nuclear scientists, we sometimes force an atom to do this by playing with the neutron-proton ratio. And that's the basis of nuclear power. Lastly, you need to be able to calculate half-life, or the mass of a sample after a particular number of half-lives, or the initial mass of a sample. The mass of the sample that you are ending with is going to equal the initial mass times 1/2 raised to the time elapsed divided by half-life. On multiple choice tests, on multiple choice questions, it will typically be whole half-lives, and you can just do it the way you did it in baby chem. In AP, you might have to use this formula to calculate a half-life or a quarter half-life, but this should lead you the right way. We will work with this in class tomorrow.